In this video, we're going to cover the confidence interval estimate for the mean when the standard deviation of the population is unknown. So previously we had assumed that we knew the standard deviation of the population, but that's not very likely in practice. What we can do, though, is we can find a sample and calculate some statistics from that, including the sample standard deviation. So previously, we had defined our z-score, is equal to the sample mean minus the population mean divided by the population standard deviation over the square root of the sample size. So we're going to define something similar called a t-value, which is the same formula except for we use the sample standard deviation instead of the population standard deviation, because that's something we could actually calculate. Related to all of this, we're going to end up using a term called the degrees of freedom. The only thing you really need to worry about is what is the degrees of freedom. That is n minus 1. It's our sample size minus 1. But where does that terminology, degrees of freedom, come from? So if we're trying to calculate our sample standard deviation, then we have to calculate the variance before that, right? We just take the square root to find our sample standard deviation. Well, to calculate our variance, we must already know what the mean is. So if we have n values, or specifically, what if we had 10 values that we were trying to sample, and we knew the mean already, right? We have to know what the mean is to calculate what the variance is. So if we already knew the mean, then once we know 9 of those 10 values, that 10th value is forced to be something, right? Because we know what the mean is, right? If we know 9 of those values and we know what the mean is, which is just the sum of the 10 values divided by 10, then once we know the first 9, we know what the 10th value has to be if we know what the mean is. So that's why our degrees of freedom is n minus 1. We have 9 values that can vary, but that 10th value is set once we know the first 9. So that's what that's referring to. It's where that terminology comes from. But essentially, we're just going to be using this terminology, degrees of freedom, and this n minus 1 to help us determine what our t value is later for our confidence interval. Now, how does all of this fit together? Well, our t distribution is similar to the normal distribution. So I've got a picture here. Our normal distribution is written here. It's drawn here. That's what our normal distribution looks like. We're all familiar with that at this point. Our t distribution is a very similar shape, except that it's a little flatter here, right? The tails have more area under them, but the center has a little bit less area, so it's not quite as high here. So this is what our t distribution will look like. It has a very similar shape. The higher the sample size, so the higher the sample size, the closer this t distribution will start to approximate the normal distribution. So since it has a similar shape, we're going to do the problem in a similar way to what we did previously when our population standard deviation was known. So, how did we do that before? Well, before we had the confidence interval is, and then we had some formula here that looks exactly the same, except we had a z value and the population standard deviation. Instead, now we use a t value, and, this should be plus or minus, excuse me, and we use the sample standard deviation. So this is how we calculate our confidence interval, using this formula right here. This is the formula we're going to use every single time here in this section. And what is T? T depends on the degrees of freedom and the desired cumulative probability. So we're going to work this out in pretty much the exact same way that we did when we knew what the population standard deviation was, except now we're using the sample standard deviation and a t-value that we get from a different chart. Okay, so let's do one example. So let's suppose that if we knew what our mean was, and that was that our sample mean was 75, the sample standard deviation is 24, and our sample size is 36. And assuming the population is normally distributed, then we're going to construct a 95% confidence interval estimate for the population mean. Well, here are degrees of freedom is equal to 36 minus 1, or 35. And our cumulative probability, right, if we recall, we had, if we wanted 95% confidence, that meant 95% of values was in between this region, and below we had 2.5%, and above here we had 2.5%, so that was outside of it. So what this meant was the z-score we had used here was for a cumulative probability of 97.5%, or 0.0975. Oh, sorry. Oops. Not 0.0, just 0.975 as our cumulative probability. Okay. So we're going to do the same thing, except we're going to use our t-chart. So if you go to a t-chart, you're going to find the row with degrees of freedom 35. And then we're going to go to the cumulative probability of 0.975. And when we look for that, we find that our associated t-value is 2.0301. And then we just want to use this formula here with t equal to 2.0301 and the sample mean 75, the sample standard deviation 24, and our sample size 36. So what this tells us is our confidence interval is 75 plus or minus 2.0301 times 24 over the square root of 36. In other words, our interval is 75 minus 2.0301 times 24 over square root of 36 is 24 over 6, so times 4. And this is going to be equal or less than our population mean, right? We're trying to estimate what our population mean is. Oops, sorry, that was off the video. And then equal or less than 75 plus 2.0301 times 4. And you can finish calculating that out with a calculator and be able to determine what that interval is. But that is it for this video.